The Earth hurtles through space at nearly 67,000 miles per hour. Though no wind touches our faces, no sensation of speed disturbs our sleep, this silent velocity, so constant we have never felt it, is the only thing keeping us gently tethered to the ground beneath us. What would unfold if that invisible motion simply ceased? If our planet hung suddenly still against the dark fabric of the cosmos? This is a question worth turning over slowly, letting the mind wander through consequences both strange and quietly immense. If these gentle wanderings help carry you toward rest, a subscription means more such journeys will find their way to you. The stillness of space holds many secrets, and this particular imagining asks us to consider forces we rarely notice. The physics of motion and gravity and atmosphere all woven together in ways that reveal how delicately balanced our existence truly is. And here, in the quiet, we begin. Tonight, as you settle into the quiet stillness of your bed, with the familiar weight of blankets gathered about you and the soft darkness pressing gently at the windows, there is something rather remarkable happening that you cannot feel at all. Something so constant and so complete that it has become invisible to your senses, much like the way we forget the sensation of our clothes against our skin after wearing them for only a few minutes. You are moving, at this very moment, at speeds that would seem utterly impossible if you were told about them in any other context. And yet here you lie, perfectly comfortable, perhaps with a pillow adjusted just so beneath your head, feeling nothing of this tremendous cosmic journey, not the slightest breeze, not the faintest vibration, not even the gentlest sensation of drift. This is the stillness we never notice, the profound calm that conceals one of the most astonishing facts about our existence on this small blue planet. Let us begin with the most familiar of our motions, the one that gives us our years and our seasons, the patient circuit that Earth traces around our sun. At this very moment, as you breathe slowly and feel the comfortable heaviness beginning to settle into your limbs, our planet is traveling through space at approximately 30 kilometers every single second, which is to say about 107,000 kilometers every hour, a velocity so tremendous that if you could somehow watch Earth from a fixed point in space, you would see it streak past like a pale blue marble launched from some cosmic sling. This speed is roughly 90 times faster than a rifle bullet, and yet you feel absolutely nothing of it. Nothing at all. Just the familiar stillness of your bedroom. The quiet tick of a clock perhaps, the distant murmur of the world settling into sleep outside your window. But this orbital dance around the sun is merely the beginning of our journey. For our entire solar system, that family of planets and asteroids and comets and dust that we call home, is itself moving through the Milky Way galaxy at a considerably greater speed. The sun, with all its attendant worlds trailing along like ducklings behind their mother, travels at approximately 230 kilometers per second around the vast center of our galaxy, a journey so immense that it takes roughly 230 million years to complete a single orbit. At this velocity, we are moving more than 800,000 kilometers every hour, and still you feel nothing. Still the tea in your cup would remain perfectly level. Still the dust motes would drift lazily in any shaft of moonlight that happened to fall across your room. And even this is not the end of our cosmic velocity, for the Milky Way itself, that vast pinwheel of 400 billion stars that we call our galaxy, is hurtling through the universe at approximately 600 kilometers every second, drawn by gravitational forces toward a mysterious region that astronomers have given the rather evocative name of the Great Attractor. This massive gravitational anomaly lies some 150 million light-years away in the direction of the constellation Centaurus, and it pulls our galaxy, along with thousands of others in what is called the Laniakea supercluster, toward it with patient, inexorable persistence. 600 kilometers every second means that in the time it takes your heart to beat just once, our entire galaxy has moved roughly 600 kilometers through the cosmic void. And yet the stars appear fixed in the sky tonight just as they appeared to your grandparents, and their grandparents before them, unchanged and unchanging in their familiar patterns. The question of why we cannot feel these tremendous velocities occupied the mind of one of history's most remarkable thinkers, a man named Galileo Galilei, who in the year 1632 published a work called Dialogue concerning the two chief world systems. In this book, which was written as a conversation between three fictional characters discussing whether the Earth moved around the Sun or remained fixed at the center of the universe, Galileo presented a thought experiment that remains elegant and illuminating nearly 4 centuries later. He asked his readers to imagine themselves below deck on a large ship, in a cabin with no windows, while the ship sailed smoothly across a calm sea at constant speed. In such a situation, Galileo observed, there would be absolutely no experiment you could perform, no observation you could make, that would tell you whether the ship was moving or standing still. If you dropped a ball, it would fall straight down to your feet, not lagging behind as the ship moved forward beneath it. If you threw a ball to a friend across the cabin, it would travel through the air just as it would on solid land. Fish swimming in a bowl of water would swim with equal ease in any direction. Butterflies would flutter about without being thrown against the stern of the ship. Everything would behave exactly as it would if the ship were moored at the dock, perfectly stationary. This observation, which we now call Galilean relativity, explains why you feel nothing of Earth's tremendous journey through space. There is no wind rushing past because the atmosphere moves with us, part of our planetary vessel just as surely as the cabin walls moved with Galileo's imaginary ship. There is no sensation of acceleration because our velocity, though immense, remains very nearly constant, changing so slowly and so gradually that the forces involved are far too gentle for our bodies to perceive. We are all of us passengers below deck on a cosmic ship, surrounded by everything we have ever known, unable to detect our motion through the universe by any sensation available to our unaided bodies. The ancient Greeks, those patient observers of the heavens whose contemplations laid the foundations for so much of our understanding, wrestled with these questions more than 2,000 years before Galileo committed his thoughts to paper. Among them was a man named Aristarchus of Samos, who lived in the 3rd century before the Common Era, and who proposed something quite radical for his time, namely that the Earth was not the fixed center of the cosmos but rather a planet that moved around the Sun. Aristarchus reasoned carefully about the relative sizes and distances of the Sun and Moon, and concluded that since the Sun was so much larger than the Earth, it made more sense for the smaller body to orbit the larger one, much as it would seem strange for a great ship to circle around a small rowboat. His ideas did not gain widespread acceptance in his lifetime, partly because his contemporaries could not explain why, if the Earth truly moved, we felt nothing of this motion, and why the stars did not appear to shift in the sky as we traveled around our orbit. These were reasonable objections, and it would take many centuries before astronomers could measure the subtle parallax of nearby stars and before natural philosophers like Galileo could explain the absence of any felt sensation of motion. There is a way, however, to measure Earth's absolute motion through the universe, a method that does not rely on our physical sensations but rather on the ancient light that fills all of space, the faint afterglow of the Big Bang itself. This radiation, which we call the cosmic microwave background, was first predicted in the 1940s and discovered accidentally in 1965 by two American radio astronomers named Arno Pentjes and Robert Wilson, who initially thought the persistent static in their antenna might be caused by pigeon droppings. This background radiation fills the entire universe and arrives at Earth from every direction in the sky. A nearly uniform glow with a temperature of about 2.7 degrees above absolute zero. However, and here the story becomes quietly beautiful in the way that scientific discoveries so often do, when astronomers began to study this cosmic background radiation with greater precision in the 1970s. Using instruments carried aloft by high-altitude balloons and early satellite missions that preceded the famous Cosmic Background Explorer spacecraft, they discovered that the radiation was not quite uniform after all. There was a slight asymmetry, a dipole as the scientists called it, meaning that the radiation appeared very slightly warmer in one direction of the sky and very slightly cooler in the opposite direction. This asymmetry, first clearly measured in 1977 by a series of careful experiments, revealed something profound about our motion through the universe. The explanation for this dipole is wonderfully simple once you understand it. When you move toward a source of light, the light appears slightly blur, its wavelength compressed by your motion toward it, and when you move away from a source of light, the light appears slightly redder, its wavelength stretched by your receding motion. This is the Doppler effect, the same phenomenon that makes an ambulance siren sound higher in pitch as it approaches you and lower as it drives away. The cosmic microwave background dipole showed that Earth, and our entire solar system, and indeed our whole local group of galaxies, is moving through space at approximately 370 kilometers per second in the direction of the constellation Leo. This measurement gives us something remarkable, a kind of absolute speedometer for our journey through the cosmos, a way of knowing our velocity not relative to the Sun or to the center of the galaxy, but relative to the universe itself, or more precisely, relative to the reference frame in which the cosmic microwave background appears most nearly uniform. And so tonight, as you lie in the gentle embrace of gravity, feeling the familiar and comforting weight of your own body pressing softly into the mattress, you might consider the curious fact that in the time it takes you to read a single sentence of this narration, perhaps 10 or 12 seconds if you read at a comfortable pace, you have traveled approximately 900 kilometers through space, without spilling your tea if you happen to have a cup beside you, without disturbing the cat if one happens to be sleeping at the foot of your bed, without ruffling a single page of a book left open on your nightstand. 900 kilometers, which is roughly the distance from London to Munich, or from Sydney to Brisbane, traveled in the space of a few quiet heartbeats, and you felt nothing at all, nothing except perhaps the pleasant heaviness of approaching sleep. This is the nature of our cosmic situation, this perfect stillness that conceals such tremendous motion, this calm that wraps itself around velocities that would seem purely fictional in any other context. The stars will slowly overhead through the seasons not because they move in any way we can perceive, but because we are tilted travelers on a spinning world that itself orbits a star that itself orbits a galactic center that itself falls through the universe toward gravitational mysteries we are only beginning to understand. And yet here you are, warm and still, the room around you perfectly quiet, the night pressing soft and dark against the windows, everything exactly as it should be, as it has always been, as it will continue to be through all the countless kilometers of your sleeping journey through the cosmos. The ancient observers who first looked up at the sky and wondered about the nature of the heavens would perhaps be astonished to learn how fast we travel, but they would not be surprised, I think, to learn that we cannot feel it. They knew, as we know, that the night sky has a quality of stillness that transcends any mere measurement, a peace that settles over us regardless of what instruments might tell us about our velocity. The stars do not rush past. The moon does not streak across the sky. The constellations hold their shapes from generation to generation, patient and familiar, and in this constancy there is a kind of comfort that no amount of scientific knowledge can diminish. So as you settle deeper into sleep, let this thought drift with you, that you are moving and still at the same time, that you are hurtling and resting, that the great journey and the perfect peace are one and the same thing, and that there is nowhere you need to go, nothing you need to do, only the gentle continuation of a voyage that began long before you were born and will continue long after this quiet night has passed into morning. The question of what might happen if our planet simply stopped moving through the vastness of space is not the sort of thing most people find themselves pondering during their ordinary days. And yet it turns out to be a question with a rather long and distinguished intellectual history, one that stretches back through centuries of careful thinking about the nature of motion itself, and about what it truly means for something to be still or to be in motion when the universe offers no obvious signposts, no painted lines on some cosmic roadway, nothing that might serve as an absolute and unchanging point against which all other movements could be measured. The story begins, as so many stories in physics do, with Isaac Newton, who in the year 1687 published his great work known as the Principia Mathematica, a book that laid out the laws of motion and gravitation with such precision that they would guide scientific thinking for more than 2 centuries, and in many practical applications continue to guide it still. Newton was deeply concerned with understanding what motion really was, not merely in the everyday sense of watching a cart roll past or a leaf drift on the wind, but in the most fundamental sense possible, and he wanted to know whether there existed such a thing as absolute motion, motion that was real and true regardless of who might be observing it or from what vantage point they might be looking. To explore this question, Newton devised a thought experiment involving a bucket filled with water, a simple and homely image that nonetheless carried profound implications. He asked his readers to imagine a bucket suspended by a rope that had been twisted many times, so that when released the bucket would begin to spin. At first, when the bucket starts turning, the water inside remains relatively still, its surface flat and calm, because the water has not yet begun to move with the bucket. But gradually, as the friction between the bucket's walls and the water takes effect, the water too begins to rotate, and as it does so, it climbs up the sides of the bucket, forming a concave surface, higher at the edges and lower in the middle. Now here is what Newton found so interesting about this arrangement. The shape of the water's surface, that curved and hollowed form, seemed to indicate that the water knew, in some sense, that it was rotating. It was not rotating relative to the bucket, because by the time the surface became concave, both bucket and water were spinning together at the same rate. And yet the water behaved differently than it had when it was still. Something was causing that curvature. Some force was pushing the water outward toward the walls, and Newton concluded that this something must be rotation with respect to absolute space itself, a kind of invisible and universal reference frame against which all true motion could be measured. This idea of absolute space was elegant in its way, providing a fixed backdrop against which the movements of all objects in the universe could be defined, but it also carried a certain troubling quality, because this absolute space could never be directly observed or measured. It was, by its very nature, invisible and intangible, detectable only through its effects on rotating or accelerating objects. The bucket experiment suggested that absolute space was real, that it existed, but it offered no way to point to it or to mark out its coordinates. Nearly 200 years later, in 1883, the Austrian physicist and philosopher Ernst Mach published a book called The Science of Mechanics, in which he subjected Newton's ideas about absolute space to careful and somewhat skeptical scrutiny. Mach was troubled by the notion of a space that could not be observed, and he proposed an alternative way of thinking about the bucket experiment that did not require any invisible absolute framework. Mach suggested that perhaps the water in Newton's bucket was not rotating with respect to some abstract and undetectable absolute space, but rather with respect to all the distant matter in the universe, the stars and galaxies and everything else scattered across the cosmos. In this view, it was the gravitational influence of all that distant matter, somehow reaching across the vastness of space, that determined what counted as rotation and what counted as stillness. If you could somehow remove all the distant stars and galaxies, Mach speculated, perhaps the concepts of rotation and acceleration would lose their meaning entirely, and the water in the bucket would have no way of knowing whether it was spinning or not. This idea, which came to be known as Mach's principle, was never developed by Mach himself into a precise mathematical theory, and it remained somewhat vague and philosophical in character, but it planted an important seed. It suggested that motion might be fundamentally relational, that it might only make sense to speak of movement when there was something else to move relative to, and that the idea of motion in a completely empty universe might be meaningless or even incoherent. When Albert Einstein developed his special theory of relativity in 1905, he was influenced by this Machian way of thinking, though the theory he created did not fully embody Mach's principle in all its aspects. What Einstein showed was that uniform motion, motion in a straight line at a constant speed, was completely undetectable from within a closed system. If you were traveling in a perfectly smooth train car with the windows shuttered, no experiment you could perform inside that car would tell you whether you were moving or standing still. You could drop a ball and it would fall straight down. You could pour a cup of tea and the liquid would behave exactly as it would on a platform at rest. There was no vibration, no sense of motion, nothing at all to indicate your velocity. This principle of relativity meant that uniform motion had no absolute meaning. You could only speak of moving relative to something else, relative to the platform you had departed, relative to the landscape sliding past outside, relative to another train on a parallel track. Speed and direction were not properties that an object possessed in isolation, but relationships between objects, and different observers moving in different ways would measure different velocities for the same object without any of them being more correct than the others. Einstein's special relativity dealt with uniform motion, with objects moving in straight lines at constant speeds, and it established firmly that such motion was relative and undetectable. But the theory said less about acceleration and rotation, about the kinds of motion that do produce detectable effects, like the curvature of the water in Newton's bucket. Einstein's later general theory of relativity, published in 1915, addressed these questions in a more complete way, describing gravity not as a force but as the curvature of space and time caused by the presence of matter, and providing a framework in which Mach's ideas could be partially, though not entirely, incorporated. For many decades after Einstein, the question of what it would mean for an object to stop moving in space remained somewhat abstract and academic, because there seemed to be no practical way to define such a state. If all uniform motion was relative, and if there was no absolute space in the Newtonian sense, then the very notion of being at rest in space appeared to be meaningless, or at least arbitrary. You could always find some reference frame in which any object was at rest, simply by choosing to measure velocities relative to that object itself. But then something unexpected happened, something that gave the old question new relevance and new precision. In the 1960s, physicists discovered the cosmic microwave background radiation, a faint glow of microwave energy that permeates all of space and represents the cooled remnant of the hot, dense state of the early universe. This radiation was emitted about 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form and for light to travel freely through space, and it has been traveling ever since, stretched by the expansion of the universe into the microwave portion of the electromagnetic spectrum. The cosmic microwave background, often abbreviated as CMB, is remarkably uniform in all directions, with a temperature of approximately 2.725 Kelvin, which is to say about 2.725 degrees above absolute zero. But when scientists began to measure this radiation with greater and greater precision, they discovered that it was not perfectly uniform. There was a slight variation in temperature depending on which direction in the sky you looked, with one side of the sky appearing slightly warmer and the other side appearing slightly cooler. This variation, known as the CMB dipole, is not a feature of the radiation itself, but rather a consequence of our motion through space. We are moving relative to the cosmic microwave background, and this motion causes a Doppler shift, the same effect that makes an ambulance siren sound higher in pitch as it approaches and lower as it recedes. In the direction we are traveling toward, the microwave radiation is slightly blue-shifted, compressed to shorter wavelengths, and appears warmer. In the opposite direction, the radiation is redshifted, stretched to longer wavelengths, and appears cooler. The discovery and precise measurement of this dipole effect provided, for the first time, something that functions very much like an absolute reference frame for motion, not in the strict Newtonian sense of an invisible absolute space, but in a practical and measurable sense. The cosmic microwave background fills all of space and provides a kind of universal rest frame, the frame in which the CMB would appear perfectly uniform in all directions with no dipole variation. Any object moving relative to this CMB rest frame will observe the dipole, and the magnitude and direction of the dipole will reveal both the speed and direction of that motion. The physicist and author Paul Davies, who has written extensively about cosmology and the nature of space and time, has explored the implications of this cosmic reference frame in his work. He has noted that while the CMB rest frame does not restore absolute space in the philosophical sense that Newton imagined, it does provide a preferred frame of reference for describing motion in our universe, a frame that is defined by the physical contents of the universe itself rather than by any abstract or invisible backdrop. In 2006, the Wilkinson Microwave Anisotropy Probe, known as WMAP, a satellite launched by NASA to study the cosmic microwave background in unprecedented detail, provided extremely precise measurements of the CMB dipole. These measurements confirmed that our solar system is moving through space at a speed of approximately 370 km per second relative to the CMB rest frame, in a direction that lies in the constellation Leo. This motion is a combination of several components, including the orbital motion of our solar system around the center of the Milky Way galaxy, the motion of the Milky Way through the local group of galaxies, and the motion of the local group through the larger cosmic web of matter. The temperature difference caused by this motion, That slight warming in one direction and cooling in the other amounts to 3.346 millikelvin, which is to say about 0.003 of a degree. This is an extraordinarily small variation, far too subtle to detect with ordinary instruments, but the precision of modern satellite observations allowed it to be measured with great accuracy. And so we arrive at last at the thought experiment that forms the subject of our present discussion. What would happen if Earth's velocity through space suddenly became zero, not relative to the Sun or to the center of the galaxy or to any nearby object, but relative to the cosmic microwave background rest frame, that universal and measurable frame defined by the ancient light that fills all of space? This is a question that could not have been asked with any precision before the discovery of the CMB and the measurement of its dipole, because before then there was no agreed-upon way to define what being at rest in space would even mean. Now, however, we have a specific and well-defined rest frame to work with, and we can consider what the consequences would be if our planet were suddenly brought to a halt within it. The question is, of course, purely hypothetical. There is no known physical process that could cause such an instantaneous change in velocity, and the scenario violates several fundamental principles of physics in ways that we will gently set aside for the purposes of this thought experiment. We are interested not in how such a thing might occur, but in what we can learn about the nature of motion and energy and cosmic reference frames by imagining that it did. Let us begin with the very first fraction of a second, that impossibly brief moment when everything changes, though of course in reality such a thing could never happen, which is precisely what makes it so restful to consider here in the quiet of this evening, as we trace through the physics of an impossible event with all the gentle curiosity of examining a pressed flower in an old book. The Earth, as we have established, travels through space at approximately 370 kilometers per second relative to the cosmic microwave background radiation, that ancient light left over from the earliest moments of the universe, and this velocity is so constant and so smooth that we never feel it, much in the same way that you do not feel the rotation of the Earth beneath you as you lie there now, breathing slowly, perhaps already feeling the first soft edges of sleep beginning to gather at the corners of your awareness. But if, in some purely theoretical scenario, the Earth were to stop moving instantaneously, coming to a complete halt in the space of just 1 second, the mathematics of what would follow are rather extraordinary in their scale, though we shall examine them calmly and methodically, as one might examine the workings of a particularly intricate clock, taking note of each gear and spring without any sense of urgency whatsoever. To understand the forces involved, we must first consider what physicists call g-force, which is a measure of acceleration or deceleration relative to the acceleration we feel constantly here on Earth's surface due to gravity, that gentle and persistent pull that keeps us comfortably settled in our beds and our chairs and upon the ground beneath our feet, and which we experience as 1g, a single unit of gravitational acceleration, approximately 9.8 meters per second squared, though you need not remember that number, as it will still be true whether you remember it or not. When astronauts launch into space aboard their rockets, they experience acceleration that presses them back into their seats with a force of approximately 3 gs, meaning they feel 3 times heavier than normal, and this is considered quite manageable for healthy individuals who have trained extensively, though it does require some adjustment and careful breathing techniques, and astronauts often describe it as feeling rather like having a very large and affectionate dog lying upon their chest, though of course the dog is invisible and made entirely of physics. Now, if we were to calculate the g-forces involved in stopping the Earth from 370 kilometers per second to zero in the space of 1 second, we would need to convert that velocity into meters per second, which gives us 370,000 meters per second. And then we would divide this change in velocity by the time over which it occurs, and then divide again by 9.8 to express the result in terms of g-forces. And when we do this calculation, proceeding step by step as one might follow a recipe for a particularly soothing cup of chamomile tea, we arrive at a figure of approximately 37,755 gs, which we might round to 37,000 gs for the sake of comfortable discussion. 37,000 gs is, to put it very mildly indeed, rather a lot. And to place this in some perspective, we might consider the remarkable experiments conducted by United States Air Force Colonel John Paul Stapp in the year 1954, when the science of aerospace medicine was still young and researchers were still learning exactly what the human body could endure. And Colonel Stapp, who was a physician and biophysicist of considerable courage and scientific dedication, volunteered to ride a rocket-powered sled at Holloman Air Force Base in New Mexico, accelerating to tremendous speeds and then stopping very suddenly indeed. In his most famous run, Colonel Stapp reached a speed of over 1,000 kilometers per hour and then came to a stop in approximately 1.4 seconds, experiencing a peak deceleration of 46.2 gs, which remains to this day the highest g-force ever voluntarily experienced by a human being. And while Colonel Stapp did survive, which is rather the point of mentioning him in this context, he did experience temporary blindness due to the blood vessels in his eyes, and significant bruising, and he later remarked that he felt as though someone had hit him in the face with a large plank of wood, though his scientific observations remained meticulous throughout the ordeal, as befitting a man of his professional dedication. 46.2 gs, then, represents something close to the outer limit of human survivability under the most controlled possible conditions, with specialized restraints and equipment and medical teams standing by. And yet the scenario we are considering would involve forces approximately 800 times greater, 37,000 gs compared to 46. And so we can say with considerable confidence that this would be, from a biological perspective, rather unsurvivable, though we shall continue to examine the physics with the same calm detachment with which one might observe clouds passing across a distant hillside. The reason these forces would arise brings us to one of the most fundamental principles in all of physics, Newton's first law of motion, which Sir Isaac Newton published in his Principia Mathematica in 1687, a work written in Latin as was the scholarly custom of the time, and which states, in essence, that an object in motion will remain in motion at the same speed and in the same direction unless acted upon by an external force, and conversely, that an object at rest will remain at rest unless similarly disturbed. This principle, sometimes called the law of inertia, explains why you continue moving forward when a car stops suddenly, and why the contents of a cup tend to spill when you stop walking abruptly, and why, if the Earth itself were to stop instantaneously, every single atom of every single object upon and within it would, in a very real sense, want to keep moving at 370 kilometers per second, because that is what they were doing just a moment before. And atoms, like all matter, have no particular desire to change their state of motion without good reason. The Earth stopping would not, in this scenario, provide the atoms of your body or the atoms of the atmosphere or the atoms of the oceans with any reason to stop as well, and so they would continue forward, which is to say they would attempt to continue forward, though of course they would immediately encounter other atoms and structures and the general solidity of things, and the result would be rather catastrophic, though we are examining it only theoretically. In the same spirit that mathematicians examine infinitely long lines or perfect circles, knowing that such things do not truly exist in nature but finding them useful for understanding nonetheless. The atmosphere presents a particularly interesting case to consider, for unlike the solid matter of the Earth itself, which is bound together by chemical bonds and crystalline structures and the general cohesion of rock and metal, the atmosphere is composed of individual gas molecules that are only loosely associated with the planet by gravity, and these molecules would have even less reason to stop than solid matter, and so they would continue forward at the full velocity of 370 kilometers per second, which is to say the entire atmosphere of the Earth would become, in effect, a wind of unimaginable intensity. To put this wind speed in perspective, we might consider the speed of sound in air at sea level, which is approximately 343 meters per second, or a little over 1,200 kilometers per hour, and this speed is assigned a Mach number of 1, so that Mach 2 is twice the speed of sound, and Mach 3 is 3 times the speed of sound, and so forth. And when we calculate the Mach number of a wind traveling at 370 kilometers per second, we find that it corresponds to approximately Mach 1100, which is to say 1100 times the speed of sound, a figure so far beyond any wind that has ever blown on Earth that it requires some imagination to contemplate, though we need not strain ourselves in doing so. For comparison, the most powerful hurricanes on Earth produce winds of perhaps 300 kilometers per hour, and the fastest wind ever recorded on our planet's surface was approximately 408 kilometers per hour during Tropical Cyclone Olivia in 1996 near Barrow Island in Western Australia. And even the theoretical winds on Neptune, the windiest planet in our solar system, reach only about 2,000 kilometers per hour. And so a wind of 370 kilometers per second, which is to say 1,332,000 kilometers per hour, exists in a category entirely beyond any meteorological phenomenon we have ever observed or could observe. It is worth noting, in this gentle and meandering consideration, that the Earth's escape velocity, which is to say the speed at which an object must travel to escape Earth's gravitational pull entirely and fly off into space never to return, is approximately 11.2 kilometers per second. And since our hypothetical atmospheric wind would be traveling at 370 kilometers per second, more than 33 times the escape velocity, the atmosphere would not merely blow across the surface but would in fact leave the planet entirely, departing into space in a great expanding shell of gas, though this is perhaps a matter for a later section of our discussion, and for now we might simply note it and move on. The energy involved in this scenario is also worth considering, for when we speak of stopping the Earth from 370 kilometers per second, we are speaking of dissipating an enormous quantity of kinetic energy, which is the energy of motion, and kinetic energy is calculated using the formula 1/2 times mass times velocity squared, a relationship that the Dutch physicist Willems Gravesand helped to establish through experimental work in the early 18th century, and which remains fundamental to our understanding of moving objects to this day. The Earth has a mass of approximately 5.97 times 10 to the 24th kilograms, which is to say nearly 6 trillion kilograms, and when we multiply 1/2 of this mass by the square of 370,000 meters per second, we arrive at a kinetic energy of approximately 2.7 times 10 to the 33rd joules, a number so large that it requires some comparison to become meaningful, though even with comparison it remains rather difficult to fully grasp, which is perfectly acceptable, as many true things are difficult to grasp fully. The Sun, that great and generous star that warms our planet and makes life possible, radiates energy at a rate of approximately 3.8 times 10 to the 26th watts, which is to say 3.8 times 10 to the 26th joules per second. And if we were to calculate how long the sun would need to shine in order to output 2.7 times 10 to the 33rd joules, we would find that it comes to approximately 225,000 years of continuous solar output, meaning that the kinetic energy of Earth's motion through space, relative to the cosmic microwave background, is equivalent to more than 200 millennia of sunlight. A comparison that is perhaps more poetic than practical, but which serves to illustrate the truly astronomical scales we are considering. The science writer and former NASA roboticist Randall Munroe, in his delightful book What If?, which explores hypothetical questions with scientific rigor and gentle humor, has examined similar scenarios involving sudden stops and catastrophic decelerations. And while he has not addressed this precise situation of cosmic motion, his work on related questions, such as what would happen if the Earth stopped spinning or if a baseball were pitched at nearly the speed of light, demonstrates the value of applying careful physics to impossible situations, not because the situations could occur, but because the exercise illuminates the principles that govern the possible situations we actually encounter in our lives. And so we have traced through the first fraction of a second, that impossibly brief moment of transition, and we have seen that the forces involved would be approximately 800 times greater than any human has ever survived, and that the atmosphere would depart as a wind traveling at 1100 times the speed of sound, and that the energies involved exceed 200,000 years of sunshine. And all of this we have considered calmly and carefully, as one might consider the patterns of frost on a window or the slow drift of leaves upon a quiet pond, knowing that the universe operates according to principles we can understand even when those principles describe events we could never experience. Let us now consider, in the gentlest possible terms, what would happen in the moments following our imaginary scenario, a quiet thought experiment in which the Earth, for reasons that need not concern us too deeply, simply comes to rest relative to the cosmic background, ceasing its long journey through the dark between the stars. We have established that such an event lies firmly in the realm of imagination rather than physics, and so we may examine it with the same calm detachment one might bring to studying the patterns of frost on a winter window, knowing full well that the glass will not break, that the morning will come warm and ordinary, that nothing we discuss here shall disturb the peaceful turning of our actual world. The first thing to understand about this imaginary cascade is that it would not begin with the Earth itself, not with the rocks and mountains and sleeping villages, but rather with everything upon and within the Earth that had been moving along with it. For you see, when we speak of the Earth traveling through space at 370 kilometers per second, we must remember that this velocity belongs equally to every atom of water in every ocean, every molecule of nitrogen and oxygen in the atmosphere, every drop of molten iron deep within the outer core. All of these things move together, in perfect concert, experiencing no sensation of motion whatsoever, much as you feel no wind upon your face as you rest in your bed, despite the fact that you are hurtling through the cosmos at speeds that would seem quite impossible to any creature who had not grown up knowing them as ordinary. But in our gentle thought experiment, should the solid body of the Earth somehow come to an instantaneous halt, these other things, the fluid things, the gaseous things, the liquid metal things, would have no such obligation to stop. They would continue onward, obeying Newton's first law with perfect fidelity, maintaining their original velocity until some force acted upon them to do otherwise. And this is where our cascade begins, not with violence or drama, but with the simple continuation of motion, the stubborn persistence of momentum, which is perhaps the most fundamental stubbornness in all of physics. The oceans would be among the first to demonstrate this principle on a grand scale. Consider that the Pacific Ocean alone contains some 700 million cubic kilometers of water, and that every portion of this water had been traveling at 370 kilometers per second in the direction of Earth's motion through the Milky Way. The ocean floor, being part of the solid Earth, would stop, but the water above it would not, could not, must not, according to the laws that govern all things. The result would be a phenomenon that we might call a tsunami, though the word seems almost inadequate for what would occur, like calling a hurricane a gentle breeze or naming a mountain a small hillock. To understand the scale, let us think quietly about energy, about the kinetic energy contained in moving water. A single cubic meter of seawater masses approximately 1,025 kilograms. And when this mass moves at 370 kilometers per second, it carries kinetic energy that can be calculated using the formula 1/2 times mass times velocity squared. If you were to work through this mathematics, which we shall not trouble ourselves to do in full, you would find that the energy involved is almost incomprehensibly large, sufficient to raise the water to heights that dwarf anything in human experience or geological memory. Conservative calculations, treating the water as a simple fluid and ignoring many complicating factors that would make the reality even more extreme, suggest wave heights of 10 kilometers or more. To place this in perspective, let us think back to the Indian Ocean tsunami of December 2004, an event that many people remember and that caused such terrible loss. The waves generated by that earthquake, which released energy equivalent to perhaps 23,000 Hiroshima bombs, reached heights of approximately 30 meters in some locations, with the earthquake itself creating only modest vertical displacement of the sea floor, perhaps 15 meters at most. That event was considered among the most powerful tsunamis in recorded history, and yet its waves were 30 meters, a number we can almost visualize, a height not so different from a 10-story building or a particularly tall tree. Now consider that our imaginary cosmic tsunami would reach heights of 10,000 meters or more, a wave taller than Mount Everest, taller than any mountain on Earth. A wave that would make the Himalayas seem rather modest by comparison. The energy involved would be greater than the 2004 event by factors that strain the meaning of ordinary numbers, and the water would move not with the speed of an ordinary tsunami, perhaps 800 kilometers per hour in deep ocean, but at speeds vastly greater, carrying its incomprehensible energy toward every shoreline simultaneously. And yet, in our thought experiment, the shorelines would face far greater concerns than the arrival of water, for the atmosphere would be undergoing its own response to the sudden halt, and this response would transform the very air into something quite unsuitable for breathing, quite unsuitable indeed for any process we might recognize as gentle or familiar. Consider the air around you now, the quiet air of your room, the atmosphere pressing softly against your windows and filling your lungs with each slow breath. This air, like everything else, moves with the Earth through space, and should the Earth stop while the atmosphere continues, the air would compress against the suddenly stationary surface, piling up upon itself in a manner that physicists describe using the principles of adiabatic heating. When a gas is compressed, it heats up. This is not a dramatic claim but a simple observation that anyone who has used a bicycle pump may have noticed, for the pump grows warm in your hands as you compress the air within it. The relationship between compression and temperature is well described by mathematical equations that have been understood since the 19th century, And these equations tell us something quite remarkable about what happens when air is compressed to a very great degree. If we imagine the atmosphere, originally extending some 100 kilometers above the Earth's surface, being compressed into a much smaller space, perhaps 1/100th of its original volume as the trailing portions of air pile into the portions that have already struck the surface, the temperature would rise accordingly. The adiabatic heating equations, which relate temperature and pressure through the ratio of specific heats for the gas in question, suggest that such compression would produce temperatures of approximately 50,000 Kelvin, a number that deserves a moment of quiet contemplation. 50,000 Kelvin is nearly 9 times hotter than the surface of the Sun, which maintains a temperature of roughly 5,800 Kelvin in its photosphere. It is a temperature at which ordinary matter cannot exist in familiar forms, at which molecules break apart into their constituent atoms and atoms themselves begin to lose their electrons, becoming the fourth state of matter known as plasma. The air, in our thought experiment, would briefly cease to be air in any meaningful sense, becoming instead a shell of incandescent plasma wrapped around a planet whose surface would have no particular reason to remain solid beneath such conditions. The mathematics of adiabatic heating are derived from the first law of thermodynamics and the ideal gas law, and while real gases deviate somewhat from ideal behavior under extreme conditions, the general principle holds true across a wide range of circumstances. When you compress a gas quickly enough that heat cannot escape, as would certainly be the case in our instantaneous halt scenario, the temperature rise is proportional to the compression ratio raised to a power that depends on the gas's properties. For air, this power is approximately 0.4, which does not sound particularly dramatic until you consider that even modest compression ratios produce significant heating, and compression to 1/100th of the original volume is far from modest. But let us turn our attention now to something deeper, something that lies beneath the crust upon which we make our homes and plant our gardens and build our quiet lives. For the Earth is not solid throughout, not at all, and the things that occur in its interior would be perhaps the most profound consequences of our imaginary halt, consequences that would unfold not in seconds but in longer stretches of time, though still quite swiftly by geological standards. The discovery that the Earth possesses a liquid outer core belongs primarily to Richard Dixon Oldham, an Irish geologist who published his findings in 1906 after careful study of seismic waves produced by earthquakes. Oldham noticed that certain types of waves, called S-waves or secondary waves, which move through solid rock with reasonable efficiency, seem to be absorbed or blocked by something deep within the Earth. S-waves cannot travel through liquids, you see, because liquids do not support the shearing forces that such waves require, and so the existence of a shadow zone, a region where S-waves failed to arrive at seismograph stations, implied the existence of a liquid layer somewhere in the planet's interior. This liquid layer, the outer core, extends from approximately 2,900 kilometers below the surface down to about 5,100 kilometers, surrounding an inner core that is solid despite being even hotter, kept solid by the immense pressure at the Earth's very center. The outer core consists primarily of liquid iron, along with some nickel and lighter elements, and it circulates in slow but powerful convection currents driven by heat from the inner core and from the decay of radioactive elements. The temperature of this liquid iron is approximately 5,400 degrees Celsius, a figure that happens to be rather similar to the temperature of the Sun's surface, a coincidence that seems almost poetic, though it arises from entirely unrelated physical processes. This churning, flowing, Liquid metal generates the Earth's magnetic field through a process called the geodynamo, in which the motion of electrically conducting fluid produces and maintains magnetic fields through principles of electromagnetic induction that would be quite familiar to any electrical engineer. Without this motion, without the careful patterns of convection that stir the outer core, the magnetic field would gradually decay, leaving the Earth's surface exposed to the solar wind and cosmic radiation in ways that would be rather unfortunate for living things. In our thought experiment, should the solid Earth somehow halt while the liquid outer core continued moving at 370 kilometers per second, the consequences for this delicate system would be rather severe. The liquid iron would crash against the suddenly stationary mantle above it, creating disruptions in the convection patterns that maintain the magnetic field, sloshing and churning in ways that bear no resemblance to the orderly flows that generate our protective magnetosphere. The geodynamo would be disrupted, perhaps permanently, though in truth the question of permanence becomes rather academic when one considers the other events occurring simultaneously. It is helpful here to consider the thinness of the Earth's crust, the solid shell upon which we live and which we tend to think of as so substantial, so enduring, so reliably present beneath our feet. The crust varies in thickness depending on whether we examine the continents or the ocean floors, ranging from approximately 30 kilometers under the continents to as little as 5 kilometers beneath the deepest parts of the oceans. Taking an average of perhaps 30 to 70 kilometers seems reasonable for continental crust, though the precision matters less than the general point, which is that this solid layer is remarkably thin compared to the Earth's total radius of approximately 6,371 kilometers. The comparison that geologists often make is to an eggshell on a raw egg, and this comparison is rather apt when you consider the proportions involved. An eggshell is perhaps half a millimeter thick on an egg that might be 50 millimeters in diameter, giving a ratio of perhaps 1 to 100. The Earth's crust, at perhaps 50 kilometers thick on a planet with a radius of 6,371 kilometers, gives a ratio of less than 1%. Even thinner in proportional terms than the eggshell. And beneath this thin shell lies not the cooked, solid material of a hard-boiled egg, but the flowing, viscous, heated material of the mantle and core, much closer in character to the liquid interior of a raw egg that sloshes about when you shake it. This image of the eggshell is worth holding gently in mind as we consider what happens when the interior of such an object continues moving while the shell does not. The mantle, though not liquid in the same sense as the outer core, is nonetheless capable of flowing over geological timescales, and possesses enough fluidity that the sudden halt would not leave it sitting peacefully in place. The outer core, fully liquid, would be even less inclined to respect the sudden motionlessness of the solid Earth, and the resulting forces would be applied to the underside of that thin crust with considerable vigor. Imagine, if you will, stopping an eggshell while the liquid inside continues moving at tremendous speed. The shell would not survive this treatment, and while the Earth's crust is made of sterner stuff than calcium carbonate, the scale of the forces involved would be correspondingly greater. The liquid iron of the outer core, with temperatures matching the surface of the Sun, would find itself pressing against rock that was suddenly, inexplicably, no longer moving with it, and the rock would be forced to accept this new arrangement despite having no particular structural capacity to do so. The cascade, then, is not a single event but a series of overlapping processes, each terrible in its own quiet way, each following inevitably from the simple premise of our thought experiment. The oceans surge forward in waves that would remake the geography of every continent. The atmosphere compresses and heats to temperatures found in stars. The outer core sloshes and disrupts the magnetic field while simultaneously applying immense forces to the base of the mantle. The thin crust, that eggshell of rock that we call home, finds itself caught between forces above and below that it was never designed to withstand, because of course it was never designed at all, merely formed by processes that had no need to consider the possibility of such an event. And yet all of this remains firmly imaginary, a thought experiment pursued for the pleasure of understanding physics rather than from any genuine concern about the possibility. The actual Earth continues its journey through space with perfect steadiness, carrying us along as it has carried countless generations before us and will carry countless generations to come. The oceans rise and fall with the gentle breathing of the tides. The atmosphere presses softly against your window. The outer core churns in its ancient patterns, maintaining the magnetic field that shields us from the radiation of space. The crust holds firm beneath our sleeping forms, and will continue to do so for time spans that make human history seem like the briefest of moments. These calculations and considerations are offered not to disturb but to illuminate, not to frighten but to satisfy the quiet curiosity that sometimes wonders about the nature of things. The universe is full of forces and processes that seem violent when examined closely, and yet the overall effect, the sum of all these cosmic accountings, is the peaceful night in which you now find yourself, the soft pillow beneath your head, the gentle weight of blankets, the slow approach of sleep. The cascade we have described remains forever hypothetical, a story told by physics about a scenario that cannot occur, while the actual cascade that surrounds you, the cascade of night sounds and gentle breathing and the soft hum of the world going about its business, continues as it always has and always shall. And so we come now to consider what would happen next, in the quiet aftermath of that impossible stillness, when Earth has lost the tremendous speed that keeps it sailing along its ancient path around the Sun. You may recall that our planet travels through space at approximately 30 kilometers every single second, which is to say about 108,000 kilometers per hour. And this velocity is not merely incidental to our journey but is in fact the very thing that prevents us from falling inward, toward that great burning star at the center of our solar system. The Sun, you see, is always pulling on us, always exerting its gravitational influence across the vast emptiness that separates us, and the only reason we do not tumble toward it is that we are perpetually falling around it instead, our forward motion carrying us just far enough to one side that we miss it entirely, over and over again, in an endless curving dance that has continued for more than 4.5 billion years. But in our gentle thought experiment, that sideways motion has vanished, and Earth now hangs motionless in space, or very nearly so, held only by the invisible thread of solar gravity with nothing to counteract it. And so begins a slow, silent fall toward the Sun, a journey that would take rather longer than you might expect, because space is extraordinarily, almost incomprehensibly vast. And even falling under the relentless pull of a star, one does not traverse such distances quickly by human standards. The mathematics of this descent were first understood through the work of Johannes Kepler, the German astronomer and mathematician who published his findings in 1619 in a book called Harmonics Mundi, which translates to something like the harmony of the world, a title that reflects his deep belief that the motions of the planets followed musical and geometric principles of profound elegance. Kepler's laws of planetary motion allow us to calculate, with considerable precision, how long it would take for an object to fall from any given distance into the Sun, assuming it starts from rest. The calculation involves treating the inward plunge as a special kind of orbit, a degenerate ellipse that has been flattened entirely so that it becomes a straight line. And when we apply this reasoning to Earth's situation, beginning at our average distance from the Sun, we find that the fall would take approximately 64.5 days. This number may seem surprisingly short when you consider that we are separated from the Sun by roughly 150 million kilometers on average, but it may also seem surprisingly long when you consider that we would be accelerating continuously throughout the journey, pulled ever faster by gravity that grows stronger as we approach. It is worth pausing here to note that Earth's distance from the Sun is not constant throughout the year, but varies in a gentle oscillation that carries us closer and then farther away as we trace our slightly elliptical orbit. At perihelion, which occurs around the 3rd of January each year, we pass through our closest approach at approximately 147.1 million kilometers from the Sun center. At aphelion, which falls around the 4th of July, we reach our most distant point at roughly 152.1 million kilometers. The difference between these two distances amounts to about 5 million kilometers, which sounds like a great deal but represents only about 3% of our average orbital radius. Still, it means that if our hypothetical cessation of motion occurred in early January, we would begin our fall from a somewhat closer starting point and would therefore arrive at the Sun slightly sooner, while if it occurred in early July, we would have a marginally longer journey ahead of us. Edmund Halley, the English astronomer who is perhaps best remembered for the comet that bears his name, contributed greatly to our understanding of orbital mechanics in the early 18th century. In 1705, he published a work in which he applied Newtonian physics to the problem of predicting the return of comets, demonstrating that these seemingly erratic wanderers followed the same gravitational laws as the planets and could therefore be tracked mathematically across the centuries. His methods for calculating orbital periods and trajectories built upon Newton's foundational work and helped to establish the framework we still use today when determining how objects move under the influence of gravity. The fall time of 64.5 days that we have mentioned is a direct descendant of these calculations, refined over the subsequent 300 years but fundamentally unchanged in its mathematical bones. As Earth began its inward fall, the changes would be gradual at first, almost imperceptible on a day-to-day basis. The Sun would grow slightly larger in the sky, its angular diameter expanding by small fractions as we crept closer, and the amount of solar radiation reaching our surface would increase according to the inverse square law, meaning that at half the distance we would receive 4 times the light and heat. For the first several weeks, this brightening might be subtle enough to dismiss, a warmth that seemed unusual for the season perhaps, a glare that made the midday sky seem uncommonly harsh, but nothing that would immediately suggest the profound nature of what was occurring. The human mind is remarkably good at normalizing gradual changes, at explaining away anomalies with reference to weather patterns or seasonal variation, and so it is possible that the true gravity of the situation, if you will forgive the small play on words, might not be widely appreciated until we had already covered a significant portion of our journey. Approximately 57 days into the fall, Earth would cross the orbit of Mercury, that small and swiftly moving innermost planet which circles the Sun at an average distance of about 58 million kilometers. Mercury itself experiences surface temperatures that swing wildly between extremes, reaching over 400 degrees Celsius on its sunlit face while plunging to nearly negative 200 degrees on its shadowed side, owing to its lack of any substantial atmosphere to moderate these variations. By the time Earth passed through this region of space, we would be receiving roughly 6 times the solar radiation that we experience at our normal orbital distance. And the heating of our planet would have become severe indeed, though perhaps not yet unsurvivable in sheltered locations or during the nighttime hours when one could hide from the sun's direct glare. The sun toward which we would be falling is a rather ordinary yellow dwarf star, classified as a G-type main sequence star in the system that astronomers use to categorize stellar objects. Its visible surface, which is called the photosphere, maintains a temperature of approximately 5,772 Kelvin, which is to say about 5,500 degrees Celsius, hot enough to glow with that familiar yellow-white light that illuminates our days. This surface is not solid in any sense that we would recognize, but rather represents the depth at which the solar material becomes opaque to light, below which we cannot see even though the star continues inward for hundreds of thousands of kilometers more. The photosphere roils and churns with convective motions, vast cells of rising and falling plasma that create a granulated appearance when viewed through appropriate telescopes and filters. Beneath this visible surface, temperatures and pressures increase steadily as one descends toward the solar core, where the fundamental processes that power the sun take place. Arthur Eddington, the brilliant English astrophysicist who made so many contributions to our understanding of stellar structure in the 1920s, was among the first to work out the conditions that must prevail in the deep interior of the sun. Through careful theoretical reasoning and mathematical analysis, he determined that the solar core must reach temperatures of approximately 15 million Kelvin, hot enough for hydrogen nuclei to overcome their mutual electrical repulsion and fuse together into helium, releasing energy in the process. This nuclear fusion is the engine that drives the sun, converting about 4 million tons of matter into pure energy every single second, and it is this energy, radiating outward over thousands of years of gradual diffusion through the solar interior, that eventually reaches the surface and streams out into space as the light and heat upon which all earthly life depends. As Earth continued its fall past Mercury's orbit and deeper into the inner solar system, the sun would swell in the sky to truly enormous proportions, dominating the heavens in a way that would make our normal sun seem almost modest by comparison. The solar radiation battering our atmosphere would strip away the outer layers of gas, boiling the oceans first into steam and then dissociating the water molecules into their component hydrogen and oxygen atoms, which would themselves be blasted away into space by the intensifying solar wind. The rocky surface beneath would begin to glow with absorbed heat, softening and eventually melting as temperatures exceeded the melting points of the various minerals and compounds that make up Earth's crust. The final approach and eventual contact with the sun would release an almost inconceivable amount of energy as Earth's gravitational potential energy was converted into other forms. This quantity has been calculated at approximately 2.5 times 10 to the power of 33 joules, which is a number so large as to be essentially meaningless in everyday terms, but which we might contextualize by noting that it exceeds the total energy output of the sun over the course of an entire week. The Earth would not so much impact the sun as merge with it, our matter mixing with solar plasma and being drawn inward by the star's immense gravity, adding imperceptibly to its mass while the energy of our fall radiated outward as a brief, faint pulse of additional luminosity that would go unnoticed against the sun's normal brilliance. Throughout this entire process, which would unfold over those 6 to 4.5 days, the sun would continue its own journey through the galaxy, carrying along the remaining planets and all the other objects bound to it by gravity. From the sun's perspective, if we may anthropomorphize for a moment, it would be simply reclaiming a small wanderer that had strayed just slightly too far, gathering back a tiny portion of the primordial cloud from which it and all its planets originally formed, some 4.5 billion years ago. There is a certain poetic completeness to this image, the idea of Earth returning to the embrace of the star that gave it birth, though of course no human observers would remain to appreciate the symbolism, and the universe as a whole would take no notice whatsoever of the event. The mathematics of falling bodies under gravitational influence is really quite beautiful in its simplicity and universality, applying equally to an apple dropping from a tree and a planet spiraling toward a star. The same equations that Kepler derived from his patient observations of Mars, the same principles that Newton codified in his laws of motion and gravitation, the same frameworks that Halley applied to the wanderings of comets, all of these would govern Earth's final journey with perfect precision, each moment of the fall predictable to anyone with sufficient knowledge and calculating ability. There is something restful in this thought, the idea that even catastrophe follows orderly rules, that the universe operates according to principles we can understand and describe, even when those principles are carrying us toward dissolution. And so we may imagine Earth's long fall coming to its gentle, inevitable conclusion, our planet dissolving into the solar fires after those 64.5 days of gradual approach. The 64.5 days that began with an impossible stillness and ended with a return to the great furnace from which all the matter in our solar system originally came. But for now, we need not dwell upon that ending, for it remains comfortably in the realm of pure imagination, a thought experiment that illuminates the physics of orbital motion by considering what would happen in its absence. The real Earth continues on its ancient path, held in its orbit by that same 30 kilometers per second of sideways motion, and you may rest assured that this arrangement will persist for a very long time to come. And so we come now to a rather different kind of consideration, one that asks us to step back from the physical consequences we have been exploring and to sit quietly with a question that might seem simple at first but which reveals itself, upon patient reflection, to be extraordinarily deep. And that question is simply this: what do we actually mean when we say that something has stopped moving? And is there even such a thing as being truly, absolutely still in a universe that seems to have no fixed stage, no immovable backdrop against which all motion can be measured with certainty? This question occupied some of the finest minds in physics during the early 20th century, and it found its most profound expression in a paper published in 1905 by a young patent clerk working in Bern, Switzerland, a man named Albert Einstein who was then just 26 years old. And the paper bore the rather technical title On the Electrodynamics of Moving Bodies, which perhaps does not immediately suggest the revolutionary nature of what lay within its pages. And yet this document would fundamentally alter our understanding of space, time, and the very nature of motion itself, inviting us to reconsider assumptions that had seemed self-evident for centuries. The central insight that Einstein offered, building upon earlier work by physicists and mathematicians including Hendrik Lorentz and Henri Poincaré, was that there exists no privileged reference frame in the universe, no special vantage point from which we can declare with absolute authority that this object here is truly at rest while that object over there is truly moving. And this was a departure from the older Newtonian view which had imagined space as a kind of fixed and absolute container, a cosmic stage that existed independently of the objects and events taking place within it, providing a universal reference against which all motion could be judged. In Einstein's conception, which we now call the special theory of relativity, all motion is fundamentally relational, meaning that we can only ever speak of an object moving relative to some other object or reference frame, never moving in any absolute sense. And this has the curious and rather beautiful implication that if you are drifting through space in a sealed cabin with no windows and no vibrations and no way of detecting the outside world, there is no experiment you can perform inside that cabin that will tell you whether you are moving at tremendous speed or sitting perfectly still. Because in a very real physical sense, the distinction between those two states does not exist. This principle of relativity, as it came to be known, tells us that asking Earth to stop moving through space is not quite the straightforward request it might appear to be. Because stopped relative to what? We must ask. And there is no cosmic signpost, no fixed grid of coordinates painted on the fabric of reality, no point in the universe that nature has designated as the origin from which all positions and velocities should be reckoned. And yet, and here is where the story becomes rather more interesting and perhaps a little more comforting for those of us who prefer our universe to have at least some structure to it. There does appear to be something in the cosmos that serves as a kind of natural reference frame, not in a way that violates Einstein's principles, but in a way that emerges from the particular history and contents of our universe. And this something is the cosmic microwave background radiation, that gentle glow of ancient light that fills all of space and whispers to us of the universe's earliest moments. The cosmic microwave background, which physicists often abbreviate simply as the CMB, represents the oldest light in existence, released approximately 380,000 years after the Big Bang, when the universe had cooled sufficiently for electrons to combine with protons and form neutral hydrogen atoms, allowing photons to travel freely through space for the first time. And these photons have been traveling ever since, their wavelengths stretched by the expansion of the universe until they now register as faint microwave radiation with a temperature of approximately 2.7 Kelvin, which is to say just a few degrees above absolute zero. The discovery of this radiation is a lovely story of serendipity in science, and it begins in the year 1965 at the Bell Telephone Laboratories facility in Holmdel, New Jersey, where two radio astronomers named Arno Penzias and Robert Wilson were attempting to use a large horn-shaped antenna, originally built for satellite communications, for astronomical observations, and they encountered a persistent noise in their equipment, a faint hiss that seemed to come from every direction in the sky and which they could not eliminate no matter what they tried. They checked and rechecked their equipment. They cooled their detectors. They even removed pigeons that had been nesting in the horn antenna and cleaned away what the scientific literature delicately refers to as a white dielectric material that the birds had deposited there. And still the noise persisted, uniform and unchanging. And it was only when they learned of theoretical work being done by physicists at nearby Princeton University that they realized they had accidentally stumbled upon one of the most important discoveries in cosmology, the echo of the Big Bang itself. And for this accidental discovery, Penzias and Wilson were awarded the Nobel Prize in Physics in 1978. There is a rather charming detail worth mentioning here, which is that if you are old enough to remember television sets that received signals through antennae, and if you recall the static that would appear on the screen when the set was tuned to a channel with no broadcast, that dancing pattern of black and white specks that we called snow, then you have actually seen the cosmic microwave background radiation with your own eyes, because approximately 0.1% of that static, a small but genuine fraction, was caused not by electronic noise or atmospheric interference but by actual photons from the early universe striking the television antenna, photons that had been traveling for nearly 14 billion years only to end their journey by contributing a few specks of light to the snow on a television screen in someone's living room. The CMB was measured with far greater precision by a satellite mission called COBE, which stands for Cosmic Background Explorer, launched in 1989 and delivering its remarkable results in the early 1990s. with the most precise measurements being reported in 1992. And this mission was led by a physicist named John Mather, who would later share the Nobel Prize in Physics in 2006 for his work in characterizing the CMB spectrum with extraordinary accuracy, confirming that it matches almost perfectly the theoretical prediction for radiation emitted by an object at a single uniform temperature, the most perfect blackbody spectrum ever measured in nature. Now here is the point that connects the CMB to our discussion of motion. When we measure the cosmic microwave background radiation very carefully, we find that it is not quite the same temperature in all directions. There is a very slight difference, a pattern called a dipole anisotropy, where the radiation appears slightly warmer in one direction of the sky and slightly cooler in the opposite direction. And this difference amounts to only about 3 millikelvin, 0.003 of a degree, which is extraordinarily small but measurable with sensitive instruments. This dipole pattern is caused by our own motion through the universe, or more precisely, our motion relative to the rest frame of the CMB, because when we move toward a source of radiation, the Doppler effect compresses the wavelengths slightly and makes the radiation appear warmer, and when we move away from a source, the wavelengths are stretched and the radiation appears cooler. And from the size and orientation of this dipole pattern, we can calculate that our solar system is moving at approximately 370 kilometers per second relative to the CMB rest frame, in a direction that points roughly toward the constellation Leo. This CMB rest frame does not violate Einstein's principle of relativity, because it is not a preferred frame in the sense that the laws of physics are any different there. All reference frames remain equally valid for describing physics, but it is a natural frame that emerges from the specific conditions of our universe, defined by the matter and radiation that fill space. And if one were to ask what it would mean for Earth to stop in some absolute sense, this CMB rest frame offers perhaps the closest thing we have to an answer. It is the frame in which the ancient light of the universe appears the same in all directions, the frame in which one is at rest with respect to the average motion of everything. The study of the CMB has also revealed some curious features that remain not fully explained, and one of these goes by the rather evocative name of the axis of evil, which is not as dramatic as it sounds but refers to unexpected alignments in the patterns of temperature fluctuations in the CMB, first noticed in data from the WMAP satellite, which stands for Wilkinson Microwave Anisotropy Probe, and reported around 2005. And these alignments seem to point in a particular direction in space that happens to be roughly aligned with the plane of our solar system, which is strange because there is no reason to expect the ancient light of the universe to know anything about our solar system. And explanations for this have ranged from subtle measurement effects to local cosmic structure to proposals that challenge our basic cosmological models. And the matter remains an area of active research and gentle controversy. Beyond the CMB rest frame, there is yet another field permeating all of space that might be relevant to our thought experiment about motion, and this is the Higgs field, whose existence was confirmed in 2012 by experiments at CERN, the European Organization for Nuclear Research, through the detection of the Higgs boson, the particle associated with excitations in this field. And the Higgs field is what gives mass to the fundamental particles that make up all ordinary matter. The way this works, in a simplified picture, is that particles like electrons and quarks interact with the Higgs field as they move through space. And this interaction is what gives them their property of mass, their resistance to acceleration, their inertia, and the strength of this interaction determines how heavy the particle is. with particles that interact strongly having large masses and particles that interact weakly or not at all having small masses or being massless like photons. One might ask, in the spirit of our thought experiment, whether stopping relative to the Higgs field would change anything about how particles acquire mass. And the honest answer is that this question does not quite make sense in the way one might hope, because the Higgs field is not something that flows past us like a wind. It is present everywhere uniformly, and there is no meaningful velocity one can have relative to it. The interaction between particles and the Higgs field happens the same way regardless of how the particle is moving, and so stopping would not alter this fundamental mass-giving mechanism. This brings us back to the philosophical heart of the question, which has been explored by contemporary physicists like Lee Smolin, who has written extensively about the nature of motion, time, and the foundations of physics. And in his work, Smolin emphasizes the relational character of physical reality, the idea that the fundamental quantities in physics describe not the intrinsic properties of isolated objects but the relationships between objects. And in this view, motion has no meaning except as a relationship between things. There is no motion of a single thing in isolation, only the relative motion of things with respect to each other. This relational perspective, which traces back through Einstein to earlier philosophers and scientists like Ernst Mach and Gottfried Wilhelm Leibniz, suggests that our thought experiment about stopping Earth is not really about Earth alone, but about the entire web of relationships that connect Earth to everything else in the universe, to the Sun and the other planets, to the distant galaxies, to the cosmic microwave background radiation, and perhaps even to the quantum fields that permeate all of space. There is something quietly comforting in this view, I think, in the idea that we are not isolated objects hurtling through an empty and indifferent void, but rather participants in a vast network of relationships. Our motion defined not by our position on some cosmic grid but by our connections to everything around us, from the nearest grain of sand to the most distant quasar visible at the edge of the observable universe. And so as you rest now, perhaps beginning to feel the weight of your limbs settling into the bed and the gentle pull of sleep approaching, you might take a moment to appreciate that the question of whether we are moving or still is not entirely a question that physics can answer, because motion is relative and the universe has no fixed stage. And in a sense we are always still relative to ourselves and always moving relative to something else. And both of these statements are equally true, equally valid, equally part of the deep and beautiful structure of physical reality. The cosmic microwave background offers us one frame of reference, the afterglow of creation providing a kind of cosmic standard of rest, and the Higgs field fills all of space, conferring mass upon the particles that make up our bodies as we move through our lives, and the great web of gravitational and electromagnetic relationships connects us to everything that exists. And in this picture, stopping is not so much a physical possibility as it is a way of asking deeper questions about what motion means and what it means to exist in a universe where everything is connected to everything else. These are the kinds of thoughts that physics invites us to have, not urgent thoughts or troubling ones, but quiet contemplations that can accompany us into sleep, reminders that the universe is more subtle and more interesting than our everyday intuitions might suggest, and that even simple questions like what does it mean to stop can open doorways into profound and beautiful ideas that have occupied the greatest minds in science for more than a century. And so we arrive at perhaps the most quietly profound aspect of this thought experiment, the part where we step back from the immediate physics and allow ourselves to consider what all of this motion, this constant and imperceptible traveling through space, actually tells us about our place in the cosmos and about the delicate conditions that allow us to be here at all. Listening to these words, breathing this air, existing on this small world as it continues its ancient journey around an ordinary yellow star in the outer suburbs of a rather unremarkable spiral galaxy. There is a photograph that serves as perhaps the most humbling image ever captured by human technology. An image that puts all of our discussions about velocity and momentum and orbital mechanics into a perspective so vast that it becomes almost meditative to consider. On the 14th of February in 1990, the Voyager 1 spacecraft, which had been traveling outward through the solar system for nearly 13 years by that point, turned its camera back toward the inner planets from a distance of approximately 6 billion kilometers. This was not a scientifically necessary maneuver, and in fact there were those at NASA who considered it a waste of the spacecraft's limited resources. But the astronomer Carl Sagan had advocated for this final backward glance, this one last look homeward before Voyager continued its journey into the darkness between the stars. The resulting photograph shows Earth as a tiny point of light, less than a single pixel in size, suspended in a scattered beam of sunlight that happened to cross the camera's field of view. The planet that contains every person you have ever known, every landscape you have ever seen, every city and forest and ocean and mountain, appears in this image as nothing more than a pale blue dot, a mote of dust suspended in a sunbeam, to borrow the phrase that Sagan himself used when describing the photograph. And yet this pale blue, this seemingly insignificant speck, is moving through space at the tremendous velocities we have been discussing, orbiting the Sun, spinning on its axis, traveling with the solar system around the galactic center, all of this motion invisible in the stillness of that single frozen image. What this photograph reveals, and what our thought experiment about stopping that motion illuminates in a different way, is that Earth occupies an extraordinarily precise set of conditions within the cosmos. The very fact that we can look at that image and recognize it as our home, the very fact that there are beings here capable of building spacecraft and contemplating their own cosmic situation, depends entirely on the particular motions and positions and temperatures and chemistries that have characterized this planet for billions of years. This recognition leads us toward what philosophers and physicists call the anthropic principle, which in its simplest form observes that the universe must have properties that allow for the existence of observers, because we are here observing it. This might sound circular or even trivially obvious when stated so plainly, but the anthropic principle becomes more interesting when we consider just how narrow the range of conditions seems to be within which complex life can exist. Our thought experiment has shown us that Earth's velocity is not merely a descriptive fact about our planet, but rather a foundational condition for everything we know. If Earth were not moving at very nearly the speed it moves, if our orbital velocity were substantially different, the consequences would be catastrophic for life as we understand it. And the remarkable thing is that even the small variations in Earth's speed that do occur naturally, the slight changes in velocity that happen over the course of each year as our planet follows its elliptical path around the Sun, already produce noticeable effects on the conditions at the surface. Earth's orbit is not a perfect circle but rather an ellipse, and this means that our planet moves slightly faster when it is closer to the Sun and slightly slower when it is farther away, in accordance with the laws of orbital mechanics first described by Johannes Kepler in the early 17th century. The difference in orbital velocity between perihelion, when Earth is nearest the Sun, and aphelion, when Earth is most distant, amounts to approximately 3%. This is a small variation, just 3% faster at one time of year and 3% slower at another, and yet this modest change in speed, combined with the associated change in distance from the Sun, contributes to the seasonal temperature variations that we experience, the rhythm of winter and summer that has shaped the evolution of life on this planet and the development of human civilization. 3% might seem like a negligible difference. But when we consider that our thought experiment involves stopping Earth's motion entirely, reducing its velocity to 0% of its current value, we can begin to appreciate the scale of the catastrophe that would follow. If a 3% variation is enough to change the seasons, a 100% reduction would be unimaginably more consequential. The precise velocity at which Earth travels is not arbitrary or incidental. It is one of the fundamental parameters that makes our world habitable, and even small deviations from this velocity have real and measurable effects on the conditions at the surface. This sensitivity to orbital variations was explored in detail by the Serbian scientist Milutin Milankovic, who spent years in the 1920s performing calculations by hand to understand how small changes in Earth's orbit might affect the planet's climate over long periods of time. Milankovic identified several cycles of variation in Earth's orbital parameters, including changes in the eccentricity of the orbit, changes in the tilt of Earth's axis, and a slow wobble in the direction that the axis points, which is called precession. These cycles operate over timescales of tens of thousands to hundreds of thousands of years, and the variations they produce are quite small, far smaller than the scenario we have been imagining. And yet Milankovic proposed that these tiny orbital changes were sufficient to trigger the ice ages that have periodically covered large portions of Earth's surface with glacier. Subsequent research has largely confirmed Milankovic's hypothesis. The ice ages that have come and gone throughout Earth's history, advancing great sheets of ice across the continents and then retreating again, appear to be driven at least in part by these subtle variations in our planet's orbital motion. A slight change in eccentricity here, a small shift in axial tilt there, and the distribution of solar energy across Earth's surface changes just enough to push the climate toward a new equilibrium, to tip the balance between ice and water, between glacial expansion and glacial retreat. The Milankovic cycles, as they are now called, demonstrate that Earth's climate is exquisitely sensitive to even minor perturbations in our cosmic motion, that the difference between a temperate world and a frozen one can hinge on variations so subtle that they would be imperceptible to anyone living through them. What this tells us about our thought experiment is that Earth's motion through space is not merely a mechanical fact but an ecological one. The velocity at which we travel, the shape of our orbit, the tilt of our axis, all of these parameters interact with the sun's energy output and with the complex systems of atmosphere and ocean and ice to produce the conditions under which life has flourished here for billions of years. Change any of these parameters too dramatically and the entire system would shift, perhaps beyond the range of conditions in which liquid water can exist, perhaps beyond the range in which the chemical reactions that sustain living things can proceed. This interconnection between Earth's physical conditions and the web of life that covers its surface was given a name by the English scientist James Lovelock in 1972. Lovelock proposed what he called the Gaia hypothesis, named after the Greek goddess of Earth, which suggested that the living organisms on our planet interact with their inorganic surroundings to form a complex self-regulating system that maintains the conditions favorable for life. The Gaia hypothesis was controversial when it was first proposed, and some of its stronger formulations remain debated today. But the underlying observation that life and environment are deeply intertwined has become a foundational insight of Earth system science. According to this way of thinking, Earth is not merely a passive platform on which life happens to exist, but rather a dynamic system in which living things actively participate in maintaining the conditions that allow them to survive. Plants release oxygen into the atmosphere and remove carbon dioxide. Marine organisms build shells that eventually become limestone and lock carbon away in rock. Bacteria fix nitrogen from the air and make it available to other forms of life. These biological processes interact with the physical processes of geology and climate and orbital mechanics to produce the relatively stable conditions that have characterized Earth for most of its history. And remarkably, those conditions have remained within a range suitable for life for a very long time indeed. There is evidence, gathered from ancient crystals called zircons found in the Jack Hills region of Western Australia and dated through careful analysis published in 2001, that liquid water has existed on Earth's surface for at least 4.4 billion years. This is an almost incomprehensible span of time, during which the sun has grown gradually brighter. The continents have drifted and collided and broken apart. Asteroids have struck the surface and volcanoes have erupted and ice ages have come and gone. And yet through all of this, liquid water has persisted. Earth has maintained, through all these changes, an environment in which the essential medium of life as we know it could exist in its liquid form. This persistence is not a coincidence but rather reflects the operation of various feedback mechanisms that tend to stabilize Earth's climate over long timescales. When the planet cools, ice sheets advance and weathering of rocks slows down, which reduces the removal of carbon dioxide from the atmosphere, which eventually warms the planet again. When the planet warms, weathering increases and more carbon dioxide is removed, which eventually cools things back down. These feedbacks are not perfect, and Earth's climate has certainly fluctuated over the eons, but they have been sufficient to keep our world within the range of habitability for billions of years. And yet there is one sense in which our cosmic motion will change dramatically in the distant future. A change so vast that it makes even our thought experiment about stopping Earth's motion seem modest by comparison. Our galaxy, the Milky Way, is currently moving through space toward a neighboring galaxy called Andromeda, and in approximately 4.5 billion years, these two great collections of stars will collide and merge. When this happens, the gravitational dynamics of our stellar neighborhood will change completely, and if Earth and the Sun still exist at that time, which is not certain given that the Sun will be nearing the end of its life by then, our cosmic motion will be utterly transformed as we become part of a new and larger galactic structure. The merger with Andromeda will not be a violent collision in the sense of stars crashing into one another, because the distances between stars are so vast that actual collisions will be rare. But the gravitational perturbations will scatter stars onto new orbits, and the orderly spiral structure of our galaxy will be disrupted, eventually settling into a new elliptical galaxy formed from the merged remnants of both original galaxies. Our descendants, if any exist at that time, will see a very different night sky, and the motion of their world through space will be governed by new gravitational relationships that we cannot precisely predict. This future merger reminds us that even the cosmic motions we have been discussing are not permanent or eternal. The solar system has traveled around the galactic center perhaps 20 times since Earth formed, and it will continue this journey for as long as the galaxy maintains its current structure. But the cosmos itself is changing, slowly and inexorably, and the conditions that currently define our celestial neighborhood will eventually give way to something new. This is not a cause for alarm, given the timescales involved, but rather an invitation to appreciate the particular moment in cosmic history that we happen to occupy, a time when Earth moves through space at just the right speed, in just the right orbit, around a star that is just the right age, in a galaxy that has not yet undergone its next major transformation. What the cosmos teaches us, then, through this extended contemplation of motion and stillness, is that we are deeply embedded in a vast and ancient system of movements and relationships, and that our existence depends on the precise continuation of those movements in ways that we rarely consider in our daily lives. The pale blue dot that Voyager photographed is not merely falling through space. It is dancing, following the complex choreography of gravitational forces that have been operating since the solar system first formed from a collapsing cloud of gas and dust some 4.5 billion years ago. And that dance, which feels like stillness to us because we are partners in it, is the foundation of everything we know and are. And so we come now to the widest view of all, the gentlest zooming out that the human imagination can manage, where our small blue world becomes first a point of light, then a memory of a point, then something too small even for memory, lost among the endless scattering of stars and galaxies that make up the cosmos we call home. We have spoken at length about what might happen if Earth were to stop moving through space, and we have traced the consequences from the very intimate, the wind and the water and the ground beneath our feet, out to the orbital mechanics that govern our yearly circuit around the Sun. And now we arrive at the final perspective, the one where motion itself reveals its deepest nature, and where stopping becomes almost impossible to imagine, because everything, at every scale, is always falling, always drifting, always held in the gentle embrace of gravity's long and patient arms. Let us begin this final meditation by placing ourselves within the structure that astronomers have come to call the Laniakea supercluster, a name given in the year 2014 by the astronomer Brent Tully and his colleagues, who mapped the flows of galaxies in our region of the universe and discovered that we belong to an immense gravitational basin, a kind of cosmic watershed where hundreds of thousands of galaxies are slowly, imperceptibly drifting toward a common center. The name itself comes from the Hawaiian language, where Lani means heaven or sky, and Akea means immense or spacious, so that Laniakea translates roughly as immense heaven, which seems a fitting description for a structure that spans approximately 520 million light-years from one edge to the other. To say this distance aloud is easy enough, 520 million light-years, but to feel it, to let it settle into the mind as something real, requires a moment of patient reflection. For a single light-year is the distance that light travels in one Earth year, moving at nearly 300,000 kilometers every second, and so 520 million of these distances, laid end to end, describes a region of space so vast that the human brain can only gesture toward it, can only nod in quiet acknowledgement that such scales exist, even if they cannot be truly comprehended. Within this immense heaven, our Milky Way galaxy drifts alongside its companions, the Andromeda galaxy chief among them, and together with dozens of smaller galaxies we form what is called the local group, a modest gathering of perhaps 80 galaxies bound together by their mutual gravity. And this local group is itself part of the Virgo supercluster, which was once thought to be our largest home but which the mapping work of Tully and others revealed to be just one lobe of the still larger Laniakea structure. All of these galaxies, all of these hundreds of billions of stars contained within them, are moving, drifting, falling toward the gravitational center of Laniakea, which lies somewhere in the direction of the constellations Centaurus and Hydra, in a region that astronomers have called the Great Attractor, though what precisely lies there remains somewhat mysterious, hidden behind the dust and stars of our own galaxy's plane. This motion, this drift of galaxies across millions of light-years, is part of a still larger pattern that astronomers have mapped over the past few decades, most notably through the work of the Sloan Digital Sky Survey, which began its observations in the year 2000 and has continued ever since. cataloguing millions upon millions of galaxies and quasars, measuring their positions and distances and redshifts, and gradually assembling a three-dimensional picture of the universe's large-scale structure. What this survey and others like it have revealed is something that scientists call the cosmic web, a vast network of filaments and nodes and voids that stretches across the entire observable universe, with galaxies clustered along the filaments like dewdrops on a spider's web, and enormous empty regions between them, voids that can span hundreds of millions of light-years and contain almost nothing at all, just the faintest whisper of matter, the gentlest possible emptiness. The filaments themselves are rivers of dark matter and ordinary matter, channels along which galaxies flow and cluster, and where the filaments intersect, there we find the densest concentrations of galaxies, the great clusters and superclusters that form the nodes of the cosmic web. Our own Laniakea is one such node, one gathering point among countless others, and if we could somehow step outside the universe and look down upon it, we would see this web stretching in every direction, a structure of almost unimaginable beauty and complexity, built from the simplest of ingredients, just matter and gravity and time, playing out their patient interactions across billions of years. The observable universe, which is all of the cosmos from which light has had time to reach us since the beginning, contains within it approximately 2 trillion galaxies, a number that was revised significantly upward in the year 2016, when researchers analyzing data from the Hubble Space Telescope concluded that earlier estimates had significantly undercounted the population of small and faint galaxies in the early universe. 2 trillion galaxies, each containing anywhere from a few billion to several hundred billion stars, each star potentially hosting its own family of planets, and all of this spread across a volume of space so large that light itself, the fastest thing there is, requires 13.8 billion years to cross from the edge to where we sit, here on our small blue world, looking out at the night sky and wondering what it all means. This figure, 13.8 billion years, is also approximately the age of the universe itself, the time that has passed since the Big Bang set everything in motion. And so when we look at the most distant galaxies, we are seeing them not as they are now, but as they were in the earliest epochs of cosmic history, when the universe was young and hot and filled with the light of the first stars being born. The light that reaches our telescopes from these distant places has been traveling for nearly the entire history of the cosmos, crossing the expanding void between galaxies, redshifted by the stretching of space itself, until finally it arrives here, at our instruments, carrying with it information about conditions that existed long before our Sun or Earth or solar system had even begun to form. And what of the ultimate fate of all this motion, all this drifting and falling and gathering, the entire cosmic web with its trillion galaxies and its unimaginable spans of space and time? Here the science becomes necessarily more speculative, for we are asking questions about timescales so vast that they make the age of the universe seem brief by comparison. But the most widely accepted picture is one called heat death, a state that the universe may reach in approximately 10 to the power of 100 years, which is a 1 followed by 100 zeros, a number so large that writing it out would fill pages and pages and still convey nothing meaningful to the human intuition. In this picture, the universe continues to expand. The stars gradually burn out. The galaxies drift apart until they can no longer see one another. And eventually all matter decays. All energy spreads out to a uniform and utterly cold equilibrium. And nothing remains but the faintest possible fluctuations in an endless and featureless void. This is not a frightening picture, or need not be, for it lies so impossibly far in the future that it has no bearing whatsoever on our lives or the lives of our descendants for countless generations to come. And there is something almost peaceful in the thought of the universe eventually settling into a state of perfect equilibrium. All motion ceased, all gradients smoothed away, a kind of cosmic rest after the long labor of existence. But it is also worth noting that this is not the only possibility that physicists have considered, for there are other models of cosmic fate that suggest the universe might be cyclic, endlessly repeating, dying and being reborn in some fashion that our current understanding can only dimly perceive. One such model has been proposed by the mathematician and physicist Roger Penrose, who was awarded the Nobel Prize in Physics in the year 2020 for his work on black holes and general relativity. Penrose has suggested a framework called conformal cyclic cosmology, in which the end state of one universe, after all its matter has decayed and only radiation remains, becomes indistinguishable from the conditions that existed at the beginning of the next, so that the death of one cosmos gives rise to the birth of another, and the universe continues not in a straight line toward heat death but in an endless series of cycles, each one containing its own stars and galaxies and perhaps its own forms of life, forever and ever without end. Whether this picture is correct remains an open question, one that future observations and theoretical work may help to resolve, but it offers a certain comfort to know that even at the largest scales and longest timescales, the story of the cosmos may not be one of ending but of eternal renewal. And so we return, gently, to where we began, to the thought that we are always moving, always falling, always held. The Earth is moving around the Sun, and the Sun is moving around the center of the Milky Way, and the Milky Way is falling toward Andromeda, and our local group is drifting within Laniakea, and Laniakea is part of the cosmic web, and the cosmic web is expanding with the universe, carried along by the stretching of space itself. At no point are we still, at no point are we truly stopped, and the thought experiment with which we began this long narration, the question of what would happen if Earth suddenly stopped moving through space, reveals itself ultimately as a question about something that cannot really happen, because motion at these scales is not something imposed from outside but something woven into the very fabric of existence, inseparable from space and time and gravity and the deep structure of the cosmos. There is a famous experience that astronauts have reported, something that has come to be called the overview effect, a term coined to describe the profound shift in perspective that comes from seeing the Earth from space. One of the most eloquent descriptions of this experience came from the astronaut Edgar Mitchell, who traveled to the Moon aboard Apollo 14 in February of 1971, and who later described looking back at the Earth from the lunar surface and feeling a sudden and overwhelming sense of connection, a recognition that all the boundaries and divisions that seem so important from the ground, the borders between nations, the conflicts between peoples, the sense of separation between ourselves and the world around us, are in some fundamental way illusions, and that we are all part of a single interconnected whole, a tiny blue island of life drifting through the cosmic dark. Mitchell spoke of this experience as something close to the mystical, a feeling of unity and belonging that stayed with him for the rest of his life. And while not every astronaut has described the overview effect in quite such transformative terms, many have reported something similar, a sense that seeing the Earth from space changes something deep within them, shifts their sense of scale and significance and belonging. And perhaps this is the thought with which we can most gently close this narration, this long and unhurried exploration of what it means to move through space, what it might mean to stop, and what the cosmos looks like from the widest possible view. We are always moving, you and I, carried along by forces so vast and gentle that we cannot feel them, falling endlessly in the curved space-time that Einstein described, held in orbits within orbits within orbits, from the Earth around the Sun to the Sun around the galaxy to the galaxy within the supercluster to the supercluster within the cosmic web. And this motion is not something to fear or resist but something to rest within, like floating in a warm and gentle current, like being held by something so much larger than ourselves that resistance would be meaningless even if it were possible. The cosmos is in perpetual, gentle motion, and we are part of that motion. We are made of the same matter that swirls in galaxies and burns in stars, and there is nowhere we could go that would be outside this belonging, no stopping that would make us separate from the whole. And so, as you drift now towards sleep, let the thought of all this motion be a comfort rather than a disturbance. Let the knowledge of the cosmic web and the immense heaven of Laniakea and the 2 trillion galaxies and the light that has traveled 13.8 billion years be not a weight but a kind of blessing, a reminder that you are part of something inconceivably vast and beautiful, that you have always been moving, always been held, and that whatever happens in the small concerns of daily life, the cosmos continues its patient dance, and you continue within it, resting now, drifting now, held.